Well, one of the uses of IR spectroscopy is to distinguish between two compounds, and we can monitor reaction progress using IR. So if we had the following reaction occurring, we have this double bond, and it's moving to here. What differences would we expect to find in the spectrum? Well, for one thing, we've got hydrogens coming off here. So we would expect to find this little peak on the left side of the 3000 mark, indicating the carbon-hydrogen bond. And we would expect, as the reaction progressed, for that to disappear because there are no hydrogens off of these two carbons. So in the product, which is shown on this side, that is missing. The other thing we would expect to disappear is we would expect the carbon-carbon double bond to disappear. It occurs right here on the reactant, but it's absent in the product. You might ask yourself, why is it absent? Because this is symmetric. There's symmetry here, there's no dipole, and so there's no absorption at the carbon-carbon double bond. There's another example. We have an oxidation reaction. Here we've got, this is an alcohol. This is the oxygen, and here's our hydrogen. And in the product, we see that right here, the hydroxy. What else do we see? Well, we can notice that there are no double bonds. And in our product, we have this nice carbon-oxygen bond that's occurring right here. The hydroxy has disappeared. And so we can monitor our reaction progress in that fashion. So let's look at a few more. For this one, for A, we're going to see the disappearance of the alcohol peak. As the reaction progresses, the alcohol peak will disappear. Let me look up the numbers for that. The 3. And a very wide peak will appear in its place. It'll widen, and we'll also see this ketone appear at about 7,200. We'll expect to see the carbon-carbon bond. Okay. B, we'll have a triple bond absorbance that will disappear. And the product will absorb at, well, we'll continue to have that. I'm not sure why I've got that. Oh, I guess we've got a double bond will appear at 1600, and we'll also get sp2 hybridization at 340, because we've got hydrogens coming off here now. We don't have any hydrogens here. So here, the double and triple bonds are symmetric, so we get no absorption, but the product will have these hydrogens. And we'll be able to see them right around. Just above the 3,000, we'll see these hydrogens. Okay, so the reactant in the fourth one here will have two signals in the double bond. I'm sorry, it's the reactant that has two, yeah. So you'll see the carbon-oxygen and also the carbon-carbon. It'll be smaller and to the right. And we would expect in the reactant for this to be conjugated, and so it's a little lower than the 1720. We'd expect this one to absorb at 1720. Okay, so this is the chart that I made up. I'm going to suggest that you need to make up your own chart. These are all the absorptions. We've got our double bonds in here: carbon-carbon, carbon-nitrogen, and carbon-oxygen. In addition, we've got how the carbon-oxygen double bond moves. If it's an amide, if it's a ketone, it's just a ketone without resonance, or an ester. And this is going to be a strong absorption. A little bit to the right, above 2,000, we've got our two triple bonds, carbon-carbon and carbon-nitrogen. Then we get into the weeds. These two gold ones right here and right here are aldehydes. Remember, aldehydes look like that. They've got a hydrogen off the end of them, and they make two peaks right there that are fairly notable. We've got our carbon-hydrogen bonds in blue and pink and green. We've got our nitrogen-hydrogen bond here, and our oxygen hydrogen bond here, making an alcohol, and here, making a carboxylic acid. It looks like a bit of a mess, and that's why I suggest you really need to make your own so that you know where things are on it. It makes things a lot easier.